Welcome, everybody. So it's Friday. Is this a good thing? Be careful how you answer. So here we are. You're probably saturated from all the things that you've already learned this week. I was just talking to a few of you here and there about the stuff that was most interesting to you. And I heard everything from XML as a pox on the universe to, wow, all this stuff is so cool, I can barely wait to get my fingers in it. So we'll see what you think about the stuff we're going to cover now. Before I get started, let me ask just a quick poll of the audience, and you can sort of wave your hands to show if you agree. How many of you at home, at work, at the cottage, wherever, in the car, own a power saw? How many people? Okay, power saw. How many of you own a power sander? Okay. Finally, how many of you own a power drill? If you were looking around, you saw by far the most hands went up at that last one. That's not to say that all power tools aren't good. Obviously, many of you are into power tools. This is an interesting piece of information about this audience. But I'll bet that at least some of you, when you said that you had a power saw or a power sander, in fact, might have been talking about attachments to your drill. And that's a metaphor for some of the features that we're going to talk about, because when a couple of weeks ago we were painting some of the doors in our house, first thing my wife did is go for the drill. Well, why did she do that? Well, first, of course, she needs to take off the hardware off the doors to paint it. So it actually works very well as a screwdriver. But the next thing she wanted to do with it was mix the paint. And you'll see illustrated here on the left-hand side some attachments you can attach to your power drill to mix the paint. And to her, the most natural thing in the world to do when you start to mix paint is reach for your drill. And you can use drills for sanding, for other kinds of things. And that's not to say that sometimes you don't want a special purpose tool. But the idea is that C++ is full of drills. And that is features that are applicable in more than just one narrow use. And we're going to see that theme continue. What I'm going to talk about today is just one slide on just setting the bar so you know where our thinking is at for where C++ should grow, both as where the whole global community is going and where Microsoft in particular is interested in promoting C++. In the second part, I'm going to have about one slide each on 4 C++ features, which are in or related to the next ISO standard for C++. So among my other hats, Microsoft graciously contributes my time to run the ISO C++ committee. That means everybody else does the work and I do administrivia, but sometimes I get to write a paper too, and so I'm interested in what goes on there. We are, I'm sure all of you are. And so here's a snapshot of 4 particular features, one of which at least is already in our product today in Whidbey, but that are drills. They are useful in more than one place, and specifically they are useful in concurrency, which that last part is the bulk of the talk, about 3/4 or more. So let's start off with just one slide on ongoing themes. Where do we see C++ going, and what's in our head when we think about what's in the next version of Visual C++ and the version after that? One key theme is continue to support native and managed code equally. C++ in Whidbey is the systems programming language for .NET. It is already the systems programming language for Windows. And one of the things you saw in C++ CLI was that as we add new features, we try to apply them evenly across the type system. So we got about 3/4 of the way there in the Whidbey release for doing things like adding generics and garbage collection and support for features like that evenly across the type system. You can instantiate templates with managed types and native types, for example. And we're going to keep doing that. So look for things like, for example, further work in MFC. Whidbey already has work to integrate it with Avalon, now also known as WPF, Windows Presentation Foundation. And you're going to see further integration work. So you can use these, it's not an either or, but you can use them well together. Look for more security work, like we did for /GS, but look for much more in that area. Link, which you may have heard about from Anders' talk yesterday. I'm not going to go to it in detail, but there's a link at the end where you can find out more about Link if you haven't heard about it yet. Run, don't walk, and afterwards, of course, after the next 75 minutes. And then take a look at Anders' talk, because on your conference DVD, It's a very, very interesting and cool technology. I'm sure you've heard about it in keynotes as well, and further other kinds of support. So that's to give you a snapshot of where our thinking is, and I'm not going to talk about the first top of the slide anymore. I'm going to spend the rest of the time talking about the bottom part of the slide, which is what's happening in the open standards world. What's happening in ISO C++. There's some really cool things happening. We currently expect the next ISO C++ standard to be done and published before the end of the decade, which ain't that far away, actually. The technical work should be done in the next 2.5 years, which, considering that the first standards process took 8 years, it's already well along, and I'll show you some features that are already in ISO C++ OX. And then most of the talk is about the Concur project. Concur is a set of language and library extensions to support concurrency directly in any imperative language, and specifically I'm going to show first examples in C++. There's a pattern here, because if you look at the Link project, you look at ISO C++ OX, and you look at concurrency, you are going to see them leverage the same power tools. So those same features that are applicable to many of these same things, where I have one feature and it works to enable a lot of stuff. So let's talk about 4 of those. I'm going to start off talking about for each. So for each is something C# and Java have had a form of. It is now in C++ in our Whidbey product, and the ISO C++ committee is considering it as well for the next version of ISO standard C++. And so the motivation goes something like this. At the top half of the slide is the code we write today to iterate over an array, a collection, that kind of thing. And instead of just reading for int I equals 0, I is less than size plus I, which, you know, we're pretty good at reading that, and we just mentally do the substitution and say, oh yeah, for each element in the collection. Why can't we just say for each element in the collection? Now, that may seem like a very minor convenience. It turns out it's an important convenience, and it's not just a convenience, but it actually enables us to do some interesting things, and I'll talk about in concurrency in particular. So in the bottom half of the slide, for each int vi in v, that's syntax that you have already in the Whidbey product today in C++, and C++ OX is likely to choose a different syntax, probably more like the lower one. So interestingly, the first C++ CLI one is similar to C#, and the ISO C++ one, if it goes that way, is similar to Java of all things. But hey, it means the same thing. It's mere syntax. And we're going to see how we directly leverage this for concurrency. Before I leave the slide, the fundamental point here is that we're raising the level of abstraction. We're not forcing people to express something in low-level concepts, what you could actually say by bringing a new abstraction into the language, saying actually declaratively, here is my intent. Because as soon as you do that, boy, now you can let the language and the compiler and your tools do better work for you because you've told them what it is you're trying to do. Automatic type inference. How many of you have ever got tired of writing things like map, int of string, : const iterator? How many of you would like to just write auto? Compiler, you know what the type is. Quit holding out on me. Don't make me say it again. This is not a good use of my keyboard time. My keys are wearing out. I can't read the letters anymore. So, and then if you could just say auto, in cases where the compiler already knows the type, notice this is not a variant type. Rather what it is it says, give me the type, but don't make me repeat it. You already know what it is. Make it be that type. And then you're still statically type safe. You have the strong safety of everything now is type checked using that type. You're just not forced to incant it if the compiler already knows. So this has already been voted into the next ISO C++ standard. It was one of the first things to go in. And this is something that is directly applicable to Link and to Concur. In Link, for example, there's lots of places where the system will just invent new types for you, very complicated named types involving generics and all sorts of things like that, that A, you don't want to write all the time because it's just too painful, and second, you shouldn't have to because they're helpers that get instantiated for you on the fly and created for you. So that makes Link programming much easier, and that's why C#3 has automatic type inference. But in particular, this is very useful for Concur as well. You'll see the same feature applied by default to active Lambda functions and active Lambda functions that operate asynchronously by default. So I'll show you much more about that in a moment. Before we get to active Lambda functions, let's talk about inactive, synchronous Lambda functions. If you've done any kind of STL programming, you've probably found yourself doing something like that first code example, where, okay, I want to call findIf or sort or something. I got to pass a functor if I want something other than the default comparison, right? So I go away and I write the functor somewhere else, not even in the same function, right? Because if you try to write it in the same function, you can't instantiate a template with it because C++ has this weird little rule. So it has to be a little ways away from your code. And then when you actually write findIf, you just say findIf vbegin vend is equal to int 3. And if you give it a nice enough name, then people can probably figure out pretty easily what it does. But if you really want to know, you have to go up, find where is equal to is defined, look in the source code, and see what it actually does. This is real painful. Wouldn't it be much nicer if you could just say findIf from vbegin to vend x equals 3? And I'm showing two versions of that. One is a lambda function where, notice the braces, we're basically writing a function object on the fly to be passed around a piece of code saying, here's this piece of code, use this. And the second one is something that's even more convenient. If you don't have a bunch of statements, it's not complicated, it's just really short, a single expression. Just use a lambda expression. In fact, this syntax in the second line under x equal 3 is very similar to what you can already do today in boost lambda. Only because it's in the language, it works all the time. Boost lambda does work most of the time, but not all the time, because it's really hard to deduce things, even with template metaprogramming, about what's going on with types. And you get much cleaner error messages, and the compiler has a much better chance of helping you. This is frequently requested for ISO C++. It may or may not make it into the next ISO C++ standard, but it's already available in very similar form in Boost today as a library. It's directly leveraged in, again, link and concur, because in link, if you've used C# at all, you know the power of anonymous delegates, which are a simple form, a limited form of lambda functions. And C# 3.0 is continuing that and broadening it into full-blown lambda functions. It's really something that really makes link usable. And again, the same thing here. So this, what we're seeing here, is something much better than today's anonymous delegates, and both C# and C++ are going in this direction. You'll see how it's also very useful in concurrency programming, because very often you want to say, hey, take this piece of code and run it. And the only extra thing you want to say is asynchronously. So now this simple feature, again, is more broadly usable in different circumstances. Finally, I'm not going to use this one as much in the rest of the deck, but it's really interesting, coming in C++OX, and so you should know that it's coming at least. Bjarne, in particular, who is still active in ISO C++ standardization, has been working, among other things, very hard on concepts for templates. Think of it as constraints, type constraints for templates. Now, we know that templates have an implicit contract. You try to instantiate them with something, and they expand it out and do full type checking. It's fully type safe. Only the error messages, if you're deep down in the middle of something, how many people enjoy reading template error messages? No. Somebody's got to put up their hand. Let's try again. How many people enjoy reading template error messages? Not even. Usually, okay, there are a few people. Usually there'll be somebody who'll put up their hand just to make me keep going. Okay, if anything, we like watching other people, the people we don't really like very much, trying to decipher template error messages. So if you take a look at this first example, I have two ints, I and j. I call sort I, j. What's wrong with this picture? Well, we all know std_sort takes two iterators. It's not going to sort two values for you, and people may be unlikely to make this mistake, but people make mistakes like this all the time. And what do you get when you say std_sort I, j? Well, let me tell you, on good compilers, high-quality compilers, you get about a half a screen full of error messages that are impenetrable, indecipherable, and give you no clue whatsoever as to what you did wrong and punish you for it. On bad compilers, you can get many screenfuls of error messages. I'm thinking of one in particular that gives page after page of diagnostics for a simple error like this. Wouldn't it be nice if you could just write std_sort I, j, and the compiler tells you, hey, stupid, I and j aren't iterators. Enter concepts. The idea is that we have a first-class notion of a concept, a way of saying, here are a set of requirements on a type. And you can know at compile time whether a certain type meets that contract or not. For example, you can have a concept of a random access iterator, which is what sort dearly loves to operate on, not ints. And then you can define sort using not just any template arguments, but specifically, I will only take random access iterators. Then you get clear, friendly, and morally decent error messages like, hey, stupid, I and j aren't random access iterators. And I don't know about you, but if it were me, I would much prefer hey, stupid than the screen and a half of that really translates to hey, stupid, but doesn't tell me what's going on. So one of the nice things about this is it just makes templates a lot easier to use and removes much of the crud and lets us get to the power without the crud of templates. So in particular, one of the things that's a little annoying, people always ask is, well, I know that when Alex Stepanov designed the STL, he made it wonderfully useful and adaptable by having iterators be the glue that separates and brings together containers and algorithms. So algorithms deal in iterators. They don't care what containers they came from. Containers give up iterators, and as long as you comply with this contract, you can use any algorithm with pretty much any kind of iterator, subject to the right iterator category, and life is wonderful. I write a new algorithm, it works with vectors and decks and lists and everything else. I write a new container, it works with all the algorithms. And life is truly wonderful. This is actually a big benefit of the STL. However, in addition to having a version of sort that takes these nice iterator ranges, you know, sometimes I have a container, and it would be a lot less tedious just to say, sort this container. So instead of writing sort v begin, comma v end near the bottom, I'd like to write just sort v. Now, why can't I do that is a frequently asked question. And the answer, unfortunately, is sort of because, well, we couldn't make that work. And the reason we couldn't make that work, well, is kind of embarrassing. Think about the overloads of sort you would have. Today, there are two overloads of sort. One takes two parameters. That takes an iterator and an iterator. And the second one takes three, an iterator, iterator, and predicate, if you don't want to use the default sorting, which is less than. So, hey, why don't we just provide two overloads for containers? We provide an overload that takes a container and one that takes two parameters, a container and a predicate. And there is the problem, because now you have two function templates that take two parameters. And today, both of them can match any type. And then you get type checking later, which means they're actually not different function templates at all. They collide. With concepts, we can actually say, hey, look, I have two overloads of sort that take random access iterators. One also takes a predicate. And I have two overloads that take a container, and one also takes a predicate. And now, there's no confusion that all of these four are very different things, and you can't possibly be ambiguous in which one you're going to get. So it just makes things much cleaner where you don't get surprises in the type system. So templates are going to get much easier to use by having something that's actually much more powerful than the constraints that you can get today in .NET and Java, for example. And so this is something that as we move forward, watch as it comes into ISO C++ OX, and watch as we look to try to make this work with generics as well. So you'll have better constraints for generics. Again, leaving things even across the type system. So this one, I went a little bit longer so that you would see more of it, because you won't see as much of it in the next slides. You will see much more about active objects, active lambdas, and for eaches, and how they play in the world of concurrency. How many of you have read the Free Lunch is Over article on the concurrency revolution? Okay. Afterwards, if you haven't, Google for free lunch and concurrency. You'll find it. It's on my website. It summarizes the issue that we're facing. And if I were to summarize it in one slide, this slide is not in the deck on the DVD, but I threw it in because I stole it from a talk I'm giving next month at the Instat Fall Processor Forum, and because it really summarizes well where we are. The main takeaway from this picture is that we have, as we look at the evolution of microprocessors and the trends in microprocessors, Moore's law is the green line. That's the important thing to remember. So it's purely number of transistors. So this tracks Intel CPU introductions, and you will find similar graphs for just about every CPU flavor under the sun. No pun intended. And as that goes up, the green line shows number of transistors increasing exponentially, right? That's a logarithmic scale. And that's going to continue. It goes off the chart, and our best guess is that's going to continue at least for another decade until 2015. So life is good. We have no worries for now on Moore's law. We do have a worry on a couple of other things. In particular, we've hit the power wall. where CPUs used to be a watt, now they're 100 watts, and the only reason they're not 1,000 watts is because it's really hard to put liquid cooling systems in a thing like this. Trust me, this is warm enough on the flight down this morning when it's sitting in your laptop. You've probably had that experience too. So the effect of that has been, as a primary reason, the blue line, which shows the growth in clock rate, had hit a wall 2 years ago. If we'd gone on the original track, we would be well beyond 5 gigahertz today. We don't have that. We're still at 3 point something or less on Intel platforms, and pretty much the same is true across the board, because we've hit this hard physical limit of power. There's also other things to think about, which is current leakage and a few other things, but primarily power is the problem. In fact, if power weren't the problem, we would have just hit this a little bit later, because as soon as you get to 5 gigahertz, light doesn't have time to go across the chip in one cycle. And so you start hitting real hard limits because light ain't getting any faster than it used to be. So you can blame Einstein or you can blame whoever. It's probably Einstein's fault, most things are. But the interesting thing about that is, how many of you write primarily single-threaded applications? This is most of you. Okay. How many of you write applications that are CPU-bound at least part of the time today? Most of you. I hate to be the bearer of bad news, but you've probably noticed this already. Your application is as fast today as it's ever going to get. That's it. So the time was, the wonderful free lunch time was that we could write a program and it wasn't fast enough for the amount of data. It's CPU bound. And you could basically, and people actually did this at universities, take a sabbatical for 6 months, come back, run the same EXE on the new hardware, and it would be fast enough. That's the free lunch. The existing programs got faster on new hardware and faster still on newer hardware. And that free lunch is over for single-threaded applications. And this is why concurrency is important, because Moore's law, those transistors are still coming. And so what are CPU vendors doing? Well, instead of making deeper pipelines, that's stalled, so to speak, pardon the pun. And instead of ramping gigahertz, which they can't do anymore either, they're doing the last thing they can do, which is give you more cores. Now, notice on this chart, a Pentium could have had about a dozen 386 cores on it. A Montecito could have 1,000 Pentium cores on it. And there's a good reason that we haven't done that today and pursued other things, is because those things are easy to build, but nobody knows how to program them for client applications. The server-side applications are nicely parallelizable much of the time, but on the client, you're doing your client-side applications, it's harder. And so what we need is a real advance and a real shift in the way we program toward concurrency, and that's where people are going to need better language support, better tool support. But you know, the answer is not going to be give me a new concurrency language, because, by the way, I have this valuable source code that is already running, and I want to be able to add concurrency incrementally to it, but well, and that's what we're going to talk about for the rest of the session. So there are already some significant concurrency-related features in Visual Studio 2005, would be. There's OpenMP for loop and data parallel operations, which is an industry standard. We have memory models for concurrency for those who are doing very risky but fast kinds of coding, and that you can get guarantees. Java has also added something very similar in Java 5. You get cluster debugging and a few other features. These are already in the product we're going to ship that you've got on your, that you've got the release candidates for at this week, and that you're going to get the full version of in 2 months. The rest of this talk is about futures. And now, let me state right now, this is to give you an idea of where we're thinking. So the whole point of this, the rest of this deck, is to give you an idea of where our thinking is at. This can change. There's no product that it's tied to specifically. I'm not saying, hey, look, these features are coming in Orcus or whatever else next. But I am saying, hey, this is important. We're doing something about it. Here's the snapshot of some of the basics of what we're thinking right now, as much as will fit into an hour, to give you a flavor for what we need to do. The litmus test I use when I think of programming models, so we need higher level programming models for concurrency. If you think about it this way, back in, the 50s, people loved coding in assembler. In the 70s, they loved coding in C. And that was ever so much better because structured programming was better than, give you a higher level of abstraction than dealing with the raw assembler. But you know, OO is ever so much better Why? For building large-scale systems? Because it gives you a next level of abstractions for building very large-scale componentized systems. Doesn't mean we still don't use structured programming, but objects definitely have given us that generational advance. And you know, we were coming to conferences probably 15, 20 years ago where there were talks on what is an object and what is a virtual function. And so you can expect that starting now, we are going to be going to conferences for the next few years with talks about breathtaking topics like what is an active object, what is a future, what is a parallel loop. And so you're going to get a first taste of that perhaps today. What we're talking about is that next level of higher level of abstractions for concurrency. Like OO was to procedural programming, we need something better than threads and locks, because running explicit threads and locking is like programming and structured programming in C. It's at that same low level. And we need something higher. So an average developer will almost never need to go down and use a thread and something named thread explicitly. And B, they will use locks much less often. They'll still be necessary, but you will use locks less, and you will use them in a much more declaratively controlled way. So not all of this is going to fit into the hour, but that gives you a sense of what we need. So these are extensions to today's languages. So concur is about extending today's imperative, not functional languages. And I'm going to use C++ for examples. And we're going to support everything from web services, distributed objects, down to in-process long-lived tasks, down to very short tasks, in fine-grained concurrency for loop and data parallel operations, where technologies like OpenMP already do a little bit today. Oh, and the last point is a very important one. If you take away nothing else, take away this. 5 years from now, if you care about performance on client systems, you will need to be able to write apps with lots and lots of unused concurrency, because that is the only way that once you ship your app, it's going to run faster on next year's hardware, as there are more hardware concurrency, more hardware threads, more cores, then your app will get faster because there's all this excess latent concurrency. So the idea is you build your app that way, and we provide the ways to map those abstractions to hardware at runtime, and then right size to the hardware and use the hardware that's available. And that gets us back on the free lunch, which is the whole point of the exercise. So here's an example of why you don't want to be coding down at assembler in C, why you want something higher level to use most of the time at least. By the way, you can always drop down to thread. I just don't want you to have much reason to. Here's a double-checked locking pattern. How many of you have done double-checked locking at least once or read about it? I was talking with someone on the front who is doing antivirus software, and they have 35 threads running. So you know all about concurrency control if you're in that kind of environment, even if they're not all ready at the same time. Shared data is the problem. Locks are the best answer we've got. And when you want to avoid the cost of a lock, you try playing games like this. So the idea is we're going to have this instance pointer, and every time I get the instance, I'm going to check to see if it's been created yet. So I lazily create it the first time, say for a singleton. And then when the first guy's created it, everybody just reuses that. That way I don't have to have a lock every time I call getInstance, which would be a performance bottleneck, especially it's a global lock, and so that could serialize and convoy a lot of your system. So to avoid this, smart people have said, oh, well, I'll check the pointer. If the pointer is not null, actually that's if instance equals null, pardon the error on the slide. We're going to now acquire the lock. Now we're only going to acquire the lock if we actually need to. Then we're going to check the pointer again to see if we were racing with somebody, if somebody already got in ahead of us in between the first pointer check and us getting the lock. And then when we know we've got the lock and it's still us who's got to initialize it, we new up an object and we return it. And everybody else will avoid taking that lock, which is a wonderful idea. And people wrote code like this, and it didn't work. And the reason it didn't work was for subtle reasons. And once those were understood and fixed, it still didn't work. For subtler reasons, and once those were well understood, it broke completely in weird ways, intermittently, as always, for concurrent programs, because of still subtler reasons. And the moral of the story is you do not want to deal with memory models. You do not want to get that intimate with the processor where you have to know the intimate details of what is going on inside the processor designer's head and how cache coherency works and what memory visibility is like. For those who do enjoy programming at that level, though, and who do have need for some optimizations, Java 5 and now Visual Studio 2005, in both managed and native, have a memory model that says you can say volatile on this, and we've sort of reused the C and C++ meaning of the term. This is a likely thing that you'll see in C++OX, by the way, also, because memory model is currently work being done in ISO C++ for exactly this kind of thing. But if you say volatile, then basically the guarantees are you don't need to read the fine print, all the right stuff will happen. So people still have to write this. It's still easy to get wrong. You can forget to write volatile. You can forget to check twice and still have windows. You have to see if your compiler and platform actually support this, and if so, for which processors. And this is just too low level. People should not ever have to write code like this. Instead, wouldn't it be nice to just have a once block where you just say, compiler, I don't care how you implement this. Once, do this, and the first time through the function, and you get the details right. We're raising the level of abstraction. Or if we want to change it a little bit in the bottom right, that we can just say, change it to an initialization and get the compiler just to do initialize everything once as it should, and leverage that, but put guarantees in there. ISO C++ today does not have guarantees to make any of these things work. And ISO C++ tomorrow and Visual C++ tomorrow will. The left-hand side is something that already exists in Visual C++ 2005. So that's one example of what I mean by raising the level of abstraction. So now let me talk about specific abstractions that are broadly applicable, just like those drills. So here we are. From the 50,000-foot level, if you were to look at it from way up high above the clouds, what would you see? You would see three main sources of concurrency in your program. And there's more features besides this, but here are the ones you'll see all the time. The first is active objects. And if you've seen actor-like languages, this has been done before. Some extensions to C++, there are dozens of variants, dialects of C and C++ for concurrency that have done things like this, and some have pursued completely different ways to surface it. This seems to be the simplest thing, where you could just say, hey, a certain type is active. I'm going to make a certain object active. And what that means is I can use that object just like I do today, but when I, say, make a member function call on it, it returns immediately. And I don't wait for it to actually execute. I just keep right on going. Yes, I know. The next question is, well, what if I care about the results of it? That's number two. But for now, you call the function, and by default, you just keep right on going. It executes in parallel. And so what method calls actually are, even locally in process, is you're queuing a work item for that active object. So each active object has its queue, and each active object conceptually lives on its own thread. It might or might not be a hardware thread or a software or an OS thread, but conceptually each active object has a thread, runs on a thread, where the first message it gets is constructor, and then it just continues pumping messages that it gets, and finally at some point at the end of its lifetime comes, delete is called on it or something like that, and it's going to run the destructor, and then its thread will end. But we're tying thread lifetimes to object lifetimes, which turns out to be really cool because we already have a language that has lots of good support in the language for managing object lifetimes. The second, this is where lambda functions come in. If I can just write squigglies and say, hey, wrap up this piece of code as a function object that somebody can go execute later. Well, why couldn't that be an active object? After all, this active is a drill. It should work evenly and be useful in more than just one area. Well, so if I have active objects, I have lambda functions, why can't I have active lambdas? Well, you can. And the idea would be that you can just put arbitrary an expression or any set of statements, a piece of code, inside those braces, put active in front, and you're running it asynchronously. Now, if you care about the result, instead of getting back an int, for example, you'll get back a future int. And what that means is that, great, I spawn this piece of work off, I take the future, but it hasn't materialized yet. It's like taking a ticket in the line. And I go off and I do my other shopping, and then when I've finally done all I can do without knowing the result of this, then I come back and, if necessary, wait with my ticket. It might be that what I'm waiting for is already there and I just pick it up and don't block at all. Or it might be that now I have to wait, but at least in the meantime, I've done work in parallel. And so, so that's what you see here, in the second code example, we have two active lambdas. One is a lambda expression. One just contains lots of arbitrary code, could be 1,000 lines. And I'm going to run those asynchronously, take out two futures, and finally, I'm just going to wait for them. And the wait is explicit, and I'll explain why when we get to the details. Finally, so if I have active and lambdas, and I can have active lambdas. Well, I have active and I have loops. Could I have active loops? Well, yes, you can. In fact, the entire loop could be active, so you could say active for each, and I'll show you why that's important. But in particular, you could have just any plain old loop you like with an active body. And remember, active brace brace just means queue me up a work item. If you ever use background worker and queue user work item, this is what you're doing, but it's much less painful. You just say, hey, here's a piece of code, and just go run it asynchronously. Similarly, if I have this loop, if I have the last form there where the body is an active lambda, then I'm just saying, hey, by default, think of each loop iteration as its own work item, and go off and do it. And I can do a little bit more efficiently in the case of for each, because I know about the structure of the loop, because I have that higher level of abstraction and declarative intent. And so I'll describe that difference when we get to it, but you can also have active on the whole loop, and it can do something sensible. So that's the 50,000-foot view. Now let's go a little bit deeper. So some of this we covered, but here's the nutshell summary. Throughout this design, and every part of it, it has to be easy for people to see where they gain and lose concurrency. Today, with free threads, free threading and locks, it is just too easy to convoy and not realize this beautifully parallel code you thought you wrote actually executes serially, and you don't know until you start doing scalability testing that it's not at all what you thought. So anytime that you gain or lose concurrency, I want that to be explicit. In fact, I want that to be so explicit that you can grep for it. And the way you do it is if you grep for the word active in your code, you will find every single place in the code where you gain concurrency, where you're going to fork off some new work or enqueue a work item. And similarly, if you grep for wait, you will find every place in your code where you could potentially block. Now, in this case, if the future is already materialized on the previous slide, you may not block at all, but if you could block, you'll see wait. So that's the first point, and you'll see that throughout. So each active object here runs conceptually on its own thread. It pumps, its method calls become messages. It has a default main line. So the default main, you can write a main method on an object now. And the default one, if you don't write it, just like you get a default constructor if you don't write it, the default one just pumps all the messages, all the message calls you get in FIFO order, in the order that they're received. That's all. But you can write anything you want there and override that default behavior. Return values and out parameters are future values. I'll talk a bit more about that next slide. And then we can express thread and task lifetimes as object lifetimes. So for example, down there at the bottom, I have an active C, I call F, it's non-blocking, and I continue executing in parallel, which is wonderful. So now futures, return values and out parameters are future values. And the idea here is that I call it, it's non-blocking, but if I actually care about some output, I have to wait for the future to materialize. And so in this example, I have a future of double, and then finally, when I need it, I say, wait. Now, does anybody have any questions about this slide and the wait? There's a question that comes up every single time on this slide. Yes, thank you, somebody said it. I knew it would happen. Well, you know, why do I have to write wait? And the answer is that initially, 6 months ago, as I was first sketching this out, I thought, yeah, you know, it'd be cool if I didn't even have to say wait there. I just say do something with tote and the wait's implicit. And I reserve the right to change my mind again. But at the bottom of the slide, there are what I consider 4 really, really good reasons. Almost each one a killer reason in its own right, at least to me, as to why that wait has to be explicit. For one thing, the first point is that thing about no silent loss of concurrency, right? I saw some nods when I was talking about silently losing concurrency, so you know what that's like. Well, imagine that in potentially lots of work there in the middle, in that ... which is only one line in the slide, but you know, in reality could be hundreds, or depending on your programmers, even thousands of lines, not all in the same function, could be lots and lots of work being done. And so you, because you know exactly what you're doing, and you want the most concurrency possible, you say just future of double tote, or in fact just you can, if you make it implicit, you can probably drop the future and just say double tote equals calc tote or total orders. And then you are very, very careful to keep your hands away from that return value. You do not touch tote. You do all this other work, and then finally at the end, you do something with tote. Then you touch it. And then you could block. Now, if you could just say use tote there without a weight, and it's just implicit, you can still write that code. And I will guarantee you, dollars to donuts, Joe maintenance programmer will come in 6 months later, look at this code, put in a debug statement right after the calc total orders to put it up to some log file. It will silently compile, and you will have completely lost all concurrency you had, and there will be no obvious reason why. Because it'll just compile silently, and the wait will be silent. I think that's probably a very bad idea. And so that's one reason, probably a killer by itself to me, but I reserve the right to change my mind, that that wait should be explicit. Another reason to make the wait explicit is because it is a blocking point. For example, if you have an out parameter, you're going to pass a pointer or a reference to some place where the result's going to be stored. Now, you still have a pointer or reference. By default, you just create a shared memory, even if it wasn't shared before, because this active object and you both have pointers to this memory. The last thing you want to have happen is a race, where it's finished in the middle of your code while you're still running, and you both try to write to it around the same time. And you'll get intermittent bugs and lots of fun Saturday nights that you should be home with your wife and kids and dogs, spent debugging these programs. But I'm assuming you probably don't want to do that. If you do, I have no explanation. So if you have this wait, at the point where you say wait, you are saying, hey, I'm not doing anything. This is where it is safe to write into these lent objects, such as out parameters or any other shared state there might be. And that is powerful. Now, yes, you could argue that, well, yeah, if the wait was implicit, you could still do that. And that still bothers me as being very subtle. Third point, the same is true. You need a safe point to emit an exception. Because what if you call this method, and then it throws an exception because it couldn't do what you asked it to do? By having an explicit wait, you have an explicit point where that exception can be materialized out to you. Marshaled across and materialized out, so you have the same programming model you've all been used to, but now with active and wait, you can say when you look at those results, an exception is a possible result. One last reason, and again, this one you could probably do without the wait syntax and the future syntax, but it's much easier with. Let's say you call a method that has 3 out parameters and a return value, and these are 4 futures you're getting. You may not need to have them all materialize at once. You may hand this one off to this guy, this one off to this guy, this one off to him, and this one off to her, and they all do work, and they may be able to do lots of work and different work in parallel, and then finally they may need to block on that. But it's very important to pass futures around, and without forcing them to materialize, that's much easier to do if you're explicit about the futures and about the waiting. So I spent half of the real estate of this slide and about 5 minutes explaining that because I think it's an important point. A, it's a frequently asked question already. B, internally, because that's the only place I've talked about this before today. Secondly, it's something that shows the design philosophy that goes into these extensions, and so it's probably valuable just to get a look at, well, why would it be this way? And this seemed like an appropriate topic to delve into that into. So here's an example of how you might use this. Let's say you have 2 services, so the 2 active classes, and in this process function, you're going to call operation 1, operation 2, and these can go on concurrently. Now, you could just fire them off and then wait for the results, or you could have a timeout, right? You could have this free form of wait, where you can build an arbitrary expression consisting of futures and of some facilities we give you, like timeouts, where you can say wait for either result 1 and result 2 to materialize, or for a certain timeout of some certain amount of milliseconds to pass. And you can just declaratively say that, and then check if did result 1 and result 2 materialize. If you got them both back within a timeout, do one thing. Otherwise, maybe cancel them, because future of T has, the future pseudo template also has things on it like cancel and potentially progress reporting and things like that. It definitely has status, so you could check to see whether it's still pending, whether it's running, whether it's completed. And so that gives you a sense of how you might use futures in your code. Combining this with active lambdas you get some very interesting programming styles. Remember that I said that one of the key things that we have to be able to enable you to do is to write apps with huge amounts of unused, untapped excess concurrency. Ideally, your application should have at least hundreds of possibly concurrent operations. They wouldn't all be ready at the same time. But if there's that latent concurrency, and maybe even more than that, if you're able to write code like this where you can just make things active, and if we get the cost of queuing that unit of work down low enough and the switching to get it back low enough, especially if foo or b or new of t, the constructor, do a fair amount of work, it could make perfect sense to spin off each of those pieces of work separately, maybe do something else, and then combine the result by saying x.wait times y.wait times p.wait arrow bar or something, where you're using the new object. So this is a flavor of the kind of style that we think is worth encouraging, that it is desirable to encourage people to be able to do easily. Yes, you could write something similar to this using background worker and queue user work item, and it's not as simple as this. We need to make it a lot simpler. And again, everything I'm talking about, managed and native. So you can take that as an unsaid, unspoken thing on every single slide. So this would apply to both the managed and native worlds. Oh, and by the way, this is where automatic type inference comes in, because by the way, when I write this active lambda, well, what's its return type, for example? Well, I use auto for that. So if you just say active, it's as if you had written out the signature active auto paren, all auto params paren, and then the body. So here are some idioms that come up. You can have, you can call an asynchronous function asynchronously. We saw that first example already. In your idioms, you can call an asynchronous function synchronously just by calling wait. You can call a function synchronously, but still leave yourself interruptible, and also get yourself out of any locks you might be holding by just using active and then wait. So let's just go through that middle one again, because that second to last one, the third one on the slide, is probably the least obvious, but once you get used to the idiom, it can roll off out of your fingers. I'm going to call some long operation, and instead of calling it synchronously, just as a normal call, I queue it up as a work item and immediately wait for it. And the two benefits I get are, if I, the caller, am an active object and somebody tries to destroy me, the destructor will interrupt the wait, and so I can respond to shutdown requests. The other thing is that some long operation now is not running under any locks that I may hold. And one of the most fundamental things, if you've been to the concurrency sessions earlier, and if you've read any concurrency books on any platform, is it is bad, bad juju to call any code you don't own or control while you're holding a lock. And so this is a very nice metaphor to get to say unlock everything, to get out of underneath whatever locks you have. And here's another way of saying, the last one is how to create a callback. I've got a future, I want to do something when it materializes. Just new up, and in this case, I'll use the garbage collected new up of an active lambda. Wait for it and then do whatever you want. So you're queuing up a work item to handle the future when it materializes. So here's an example that's taken from Doug Lee's wonderful book, Concurrent Programming in Java, excuse me, 2nd edition. And the advice is to never lock when invoking methods on other objects. In general, this is a specific case of never lock. Don't even think about calling somebody else's code while you're holding a lock. By the way, why is that? Anybody want to shout it out? Deadlocks. You're prone to deadlocks. The reason is, you hold a lock, you call somebody else, he might try to acquire a lock. So far, so good. But if those two locks can ever by anybody else be acquired in the opposite order, thank you. You're deadlocked, you're hosed. So that's why when you're holding a lock, you never want to call into unknown code. Of course, this is what all of today's frameworks, including .NET and Java, do. Because they call virtual functions while holding locks in some cases, like Java Vector and .NET Sync Hash Table are two examples. And they hold a lock and call your code, which you might acquire a lock. So we need to be able to break out of that style and enable something much better. So here's an example from CPIJ, from that book. There's a class particle. It has two protected ints. And there's a sample draw function. It gets a graphics context. And then it wants to call drawRect. on that graphics contents to draw itself draw a rectangle at its position of size 10. Now, it can't just call g.drawRect x, y, 10, 10, because that would be calling somebody else's code while this class is at a lock. I didn't show it, but the draw method is synchronized in this case, and so it's holding a lock, and you don't want to do that. So instead what you do is you take copies of, you get all your work ready that you want to ship off, you take copies of your local variables in this case, of your member variables in this case, and then you go and you call this other function. And one of the things about this is that it's kind of annoying that you have to do this extra work. If you had an active object, well, first of all, you don't need to do locks at all. You don't need synchronized methods on active objects. They just don't apply, because the active objects methods already are already serialized with respect to each other on the active objects thread. He's already partitioned off by himself, so he's safe that way. But you still want to avoid blocking, and the difference between locking and blocking is only one letter, and there's a good reason for that. You get very similar problems. So all you do in this case, in the concur syntax, would be say return active drawRect, and what that does is it spins off a work item. Because I return it, it also, if anybody's waiting on the future, he has to wait for that to complete too. But now, in the meantime, the draw method finishes, and it can go on servicing other requests. It's outside of locks, and life is wonderful. Here's another example of this where it's almost the same code, but let's say that I'm getting a sync hash table, and I'm an active class shape, and somebody's saying, oh, add yourself to this sync hash table. I had better not just call add this, 42, because if I call that synchronously, the sync hash table then is going to go and it's going to call what? It's going to call get hash code by default on me, and so that's going to come back as a message to me, but I'm still waiting for it to finish, and so I'm not going to pump messages. Now, there's a couple of ways around that. One of the easiest is simply to say return active and put the same code you would have written, but just put it in active. And so basically, this is an idiom you can expect to see time and again. Just anytime you're in an active object, just do all the work you can in a return active. Just push all the work you can out of the body where you don't need to keep hold of your active object, and just push it all down into return active. And by learning that one thing, the user doesn't have to think about all the problems with calling unknown code while holding it a lock, while that code that might block and reentrancy and horrible things like that, by using that one single idiom. But he's just using active again. Just as a little bit of a break, let's compare this with how you do things today. So here's an example from the .NET Design Guidelines, the FX async pattern. The idea is if you have a piece of work that you want to be able to call asynchronously, instead of you having one function, you split it into two functions, a begin and an end version. And the begin version takes the in parameters, the end version spits out the return value, stuff like that. Then what you do, and the problems with this is it's intrusive because you have to know which functions you want to split apart, although there are ways around that part. It's still complicated for the caller because the caller has to call two things, but in the meantime, he's got to keep a cookie for the async result, and he's got to write a callback to do something with the async result when it comes back. But worst of all, this is a hand-coded pattern, and there's no language support for it. There's no checking for it. So a certain very common example that actually was in a very famous book written by a very famous author who I won't name, maybe, is to say, well, you know, if you don't need the value, you don't need to call n. The author has since blogged about that as an erratum in his book, and it's going to be fixed in future printings because, in fact, you do need to call end, even if you don't care about the result, because you might leak resources. You might be the cookie, the async result might be holding on to things that won't be collected in a timely way or at all, and you really, really do need to call end. And this is one example of why in the design guidelines it says always call end. And you might get some FX top support for this, but there's no language support. There's otherwise no tool support for it. And we'd like to do something better than brittle hand-coded patterns. This is structured programming. This is wiring up your own vtables in C. We would like objects that give us an abstraction that does this work for us. So here's an example of how you use this pattern if you're calling. In fact, this is a related version that actually makes it quite a bit easier by using C# anonymous delegates. The white code is the code I want to write. The yellow code is the code I don't want to write. What I want to do, if you follow the white code, is I want to call this sampsyncobj.square. I want to call it square method, and I want to pass 42. That's all. That's all I want to do. But here's what I have to write for it. And this is, again, a simple example. I have to create a new delegate for the square method. Then I create an async result where I'm going to keep a handle to begin invoke on that new async callback of the callback I just created, and then pass it 42 again to remind myself what this was all about later when the callback gets called. I'll show that callback on in the next build. Then I call wait handle just to wait on it, and then I wait 1. Now notice that this code doesn't actually do anything with the result. If you want to see where you actually get the results back out of square, well, notice we're creating a new async callback for this myCallback function. So you got to write this other function, which then gets called back. It takes an async result, and notice it has to look at that cookie value. Oh, 42. Okay, that's what I was doing, and remember what I wanted to do with it. Then call the end invoke to actually get the result that I wanted, and then right line, the result is whatever. Easy? How many of you have written code like this, by the way? How many of you enjoyed it? Interesting. Okay. Because this is actually fairly simple compared to what you would have to do if you didn't even have the async pattern and anonymous delegates. So here's the same code in Concur. I prefer that. It says what I want to do. I just want to call square of 42 and then wait for the result. Okay, so call square of 42. Oh, by the way, I wrap it in active to make it async. Then I do other stuff, and then I .wait for the result. And by the way, in the previous version, not only was this a lot more code, but I couldn't grep for all the places that I gain and lose concurrency. I could grep for begin invoke, and I could grep for end and for wait 1. It's not nearly as easy to see where I'm actually gaining and losing concurrency because the begin and end are in different places. The callbacks are done at different times, and it's not all together like it is here. That's just one example of how we're practically trying to make things easier. It should be easy for people to queue up work items and do work asynchronously. A word about destructor semantics. Remember I said we tie thread and task lifetimes to object lifetimes? So if I have a local object, say on the stack, I create an active object. When I call its destructor, that is the only exception. Remember I said grep for active and grep for wait, and you'll get everything? There is exactly one exception to that currently in the current thinking, and I might remove even this one, but the only exception is that when you call the destructor on an active object, by default you block. So it doesn't say wait, but by default you block. That might change, but that's the only exception right now. The reason for that, though, is it makes it very easy to express task hierarchies, task lifetimes in terms of object lifetimes and scopes. So for example, in this case, with the first example, I have active C, and then I do other work, and then the block end is an implicit join point. That's where I join back together. And similarly, if in the bottom example, if I have an active type and it has members that are active types, then the enclosing active object, its destructor will wait for the member destructors to wait until those tasks complete and agree to end their execution. And so it's very natural to express aggregations of tasks the way we already express aggregations of objects. And yes, just like in plain old C++, the way it is today, if you didn't want the task lifetime of the member to be tied to the task lifetime of the enclosing object, just do what you do today. Hold it by pointer or reference. Then you're not tied anymore. But if you want them to be related, then embed them by value, and you tie their lifetimes just as you always have. Here's another example that you can look at, producer-consumer. So as classic producer-consumer, I have a producer object that passes information to a consumer object and a main line that creates one of each until they end. And the only difference was I had to write active in 3 places. So very often, the impact on existing code hopefully will be that low to be able to add concurrency to existing kinds of code. Let me use the last 15 minutes to talk about loop and data parallel operations, which are much more fine-grained than active objects and even active lambdas. And this is something where we're going to see some examples, comparisons to OpenMP code. So by the way, how many of you have written OpenMP code or have read OpenMP? Oh, quite a few. All right. So you'll see some side by side, and you can decide for yourselves if you think this is a win or not, or if there's maybe further work we need to do. But here's a snapshot of the thinking. So we are shipping OpenMP and WDBI, so you can use it, you can rely on it. It's a stable standard, it's out there, it's useful. It's portable. It hides many details for you. These are all good things, where you can write parallel loops that right size to the actual hardware. Remember, that's a wonderful thing. That's a goal we want to achieve. I still don't really like it very much, and I don't know too many people who do. I'll tell you what I call it. And I've actually not had anybody yet disagree with me, but if you disagree with me, feel free to yell so that everybody can hear you. I think OpenMP is industrial strength duct tape. It is unquestionably industrial strength. It is unquestionably valuable. You should know about it. You should use it until something better comes along, especially because it is useful today. We would not have spent all the time we did putting it in WDBI, making sure it worked and worked well if it wasn't. But it is duct tape. It's not integrated with the language. It's tacked onto the language. Specifically, it's tacked onto Fortran and C, not C++. And that shows all over the place. So it's bolted on. It's only good for very simple kinds of for loops. It doesn't work with STL collections, for example, or with BCL collections, which would be kind of a useful thing for it to work with. And it doesn't take advantage of C++ and the superior abstractions we already have for dealing with types and type safety in C++. So in Concur, here's what you would do, and then I'll start showing examples side by side with OpenMP. Remember, there's two styles of parallel loops. You can either make the loop body, the entire body, active, which just basically means each iteration is sliced off as its own individual work item, right? So you don't change loop control variables in the body. The for statement, the control statement, is executed on the main thread, and it just parcels off work items for each iteration. Or if you actually are using a higher level of abstraction and you can tell the compiler what you meant, so you're actually doing for each, then you can make the whole loop active, and then we will chunk the work for you. That is, we can take advantage of knowing for this particular kind of container, hey, this chunk fits in your L2 cache. This chunk fits in your L2 cache, and do better things so that when you run each chunk on a different processor, you do it really efficiently. So OpenMP does many such things under the covers for you already. We'd like it to work with BCL collections, with maps, with vectors, and the STL, and things like that. And if you do want the side effects of these loop iterations, you can use a collection of futures as well. Much of the time you won't want to do that, but you can still do it if you want to. And then you can iterate over those. So here's an example. First, the non-concurrent code above goes through the array, and it just computes the average neighbor sums and just does it serially. But I've got these other cores on the system, and I'd really like to use them. Instead, what I'd like to do is to do these calculations in parallel, do part of the array on each of a team of, say, 2 worker threads, or whatever the hardware will support. And in fact, that's what OpenMP does. So the top code fragment is all you have to write in OpenMP. This is actually pretty nice. You just write pragma OMP parallel for. So this pragma, as you see it all the time, that's how it's bolted on. It's not in the language, it's all pragmas on C. But I just put the pragma parallel for and I'm done, so that's nice. In fact, just to show how nice that is, because I don't want to sound like I'm criticizing it, because I think it is valuable, if you didn't have that, the bottom code is what you'd have to write in explicit Windows style threading code, and that's not even all the code. That's just showing you need a thread function, then you need to split up the work yourself, figure out how many worker threads you want, wait for multiple objects, and there's actually more code you'd have to write. But that gives you a flavor of why you just don't want to do that, and why, if it's that hard, people won't do it. So OpenMP, definite win. That's a definite advancement of concurrent programming. The Concur code, though, that's equivalent is you put active in front and you use for each. And that has the same semantics where, just like the OpenMP parallel for knows to chunk things, and it can be very efficient about what it does under the covers, rather than just giving the worker one slice of the loop at a time, it can give them a chunk of loop iterations at a time and gain efficiency that way. The same thing active for each can do. And if you look through the OpenMP spec, and you look at all the limitations on OpenMP parallel for loops, you will see things like the iteration variable has to be an int. It can't be touched in the body of the loop. It has to be incremented, only incremented. You can't go step 2 or step of a function. That's describing for each. That's saying, I recognize that what you really meant to say was for each, but because you're using C, you couldn't write that. That's what it's saying. And that's why there's this direct parallel with active for each. Oh, by the way, that also, the active for each does have a bigger advantage because the syntax is not that big a difference. We can work with STL and BCL collections, not just arrays. And you can use it to build parallel algorithms, such as parallel transform. There's a parallel version of the transform algorithm that can do this, that you can provide. And where you use active lambdas to just say, hey, take these two ranges, add them and divide by 2 and put the result in B. So if you like STL programming, STL styles, that last one will also work for you. Here's another example. And most of these examples come directly from the OpenMP spec in their appendix for examples. So in this case, what I want to do, I'm going to get a collection of floats, an array actually, an array of floats and an array of ints of some size. And I'm going to go through them all. I'm going to add together all the floats, so I'm going to XOR all the ints. I don't know why. That was what the example was, so I thought I had to be able to write that. So in Concur, what you would do, you could actually write an active loop yourself, but in this particular case, I thought the easiest thing to do was to use the accumulate algorithm in STL, but a parallel form which uses a for each and active for each inside that just says p accumulate x starting with 0 and use addition. And notice I'm using that lambda function, that lambda expression there as well. Just add the two values. And then for b, accumulate from y starting with 0 and XOR. The code at the bottom of the screen, and this is an unfair comparison. I'm not intending to compare performance here because the top OpenMP code was an example to show how you would use it rather than an efficient way to use it. But it's worth noting that the version down below is probably more efficient too, because you're not looking at one element of this array and then one here, then one here, and one here, and one here, and one here. You're going through each array once, which is going to be more efficient and have better cache behavior unless X and Y happen to be very near each other and small in memory anyway. Here's another OpenMP example. Let's say you're going through a loop where you want to update atomically. You want to actually have the different loop iterations update some shared information. In this case, a collection, an array of buckets where it's storing counts. So it wants to update the right count, but you don't know in advance which bucket that's going to be. The top is what you write in OpenMP. You say parallel for, okay, and you actually can also say, okay, these are the things that are going to be shared. And you have to say X is going to be shared here. And then you say, oh, by the way, I want this to be atomic. I want updating X of index of I plus equals work1, some function, to be atomic. It would actually be easier, and you could do some of the same change to the OpenMP example, I think. It would be much simpler just to be able to say, hey, I want this piece of code to be atomic. And if you went to the Microsoft Research talk about concurrency topics, you will have seen some very similar syntax for software transactional memory. That is not what this is, but it could be. So if we don't have transactional memory, we can still do this. But if we get transactional memory in the future, if that research pans out, then we have another option for implementing this. But your source code doesn't care. It'll just get better in the next release when you recompile it. That's the kind of thing we can do for you under the covers because, again, this level of abstraction. So I'm going to be able to do the work in parallel, but then just serialize the updates into the array just to be sure that I'm not colliding on that shared data structure. So that gives you a flavor. And again, this was like a breeze tour through just a few core concepts. There's a bit more, but that gives you a flavor for the core concept for how to express concurrency in this kind of programming model and what it would look like, and that it can be done incrementally to your existing code bases. The idea is, you don't want to just rewrite everything to be hyper-parallel, if you can at all help it. You've got existing code that works. How do I say, hey, I don't need this result right now, and be able to start spinning off work to make an existing code base incrementally parallel well? So as a summary, the two key slides as to where our thinking is, we're still doing native and managed. C++ is still targeted as a first-class language in both native and managed, the systems programming language for .NET and for Windows. And that's going to continue with more managed support and more native support. MFC support for Windows Presentation Foundation continues to move forward. Link and other projects you'll continue to see, both for managed and for native. But also, we live in an ecosystem of a standard, an ISO standard language that is far from just Microsoft, and that's a good thing. And we believe in open standards. That's one of the reasons we participate continually in the C++ committee, have done a lot of work 2 releases ago, you'll remember, to conform to the standard, belatedly, but it was done. And so as we track new features in ISO C++ OX, it is specifically with a view to how can we use those rather than reinventing something similar to do better things like concurrency. We don't want to end up giving you one narrow feature here and a sort of similar but different narrow feature here just because the standard did one thing and no, we thought it'd be better to do something else. That doesn't get anyone anywhere. So to minimize the number of abstractions, use the drills that can be used across projects like Link, ISO C++, and concurrency to be able to bring these things together well. And the slide that summarizes the rationale for concurrency, you are already getting good tools in WDB. Learn them, use them. This is the time to get concurrency training. I hope many of you might have been able to go to the concurrency classes. There were 2 talks earlier in PDC, I believe on Wednesday. Did many of you get to go to that? If you didn't, they're on the DVD. They're a very, very good investment of 2 hours. I would highly recommend that everyone take 2 hours and go through those. That's a very good use of time. But we need programming models that are higher level, that are an OO for concurrency. And the litmus test I use is that any programming model where you deal with explicit threads, including thread pools, and you deal with explicit locks all the time, is too low level by definition. You might as well just say that's fine to get us the next 5 years, but we need something substantially better for our future to enable our very, very parallel client future. So that's what we're intended to do, extend today's languages so you can adopt these things incrementally, do things like active objects, futures, and active loops, support granularities that are very coarse-grained and external, like web services, coarse-grained but internal, like active objects that might live a long time, down to really small things like slices of loops that can be done in parallel, and try to do that pretty seamlessly so that you don't feel like you're entering a different world when you're using it here and here. Oh, active means the same thing across the board. To achieve that kind of uniformity. And then finally, once we've enabled you to build these applications with lots of latent parallelism and that you ship it, and the customer runs it on a 2-way machine today, and we scale it down to that, and the customer upgrades and runs it on a 4-way and a 16-way, and it gets better without you shipping the application again. And the customer then upgrades to 32 and 64 and 128 hardware threads, and your application gets better. That's where you need to be. That's where one of the major directions that we need to take you. And so this is some of the snapshot of thinking of where we currently are. Again, we're not tying this to any specific release or announcing it any more specifically than that. But we thought you'd like to know what the thinking was, ways that we're looking at solving these problems, and also to make you aware of them. So over the coming few years, as you realize that as you deal with those, you can see how to use existing tools and also see what's coming down the pike so you can be ready for that. So thank you very much for taking the time. We do have some time left over for questions. I'll deliberately run over 5 minutes, so please.
Yeah, hi Herb. The question I had was, do you anticipate these extensions, the concur extensions, being implemented in something like the multi-threaded runtime libraries? Or is this going to be a feature that's going to be more like a virtual machine for C++?
So the idea here is, so I think the question you're asking is this a C++ only feature? And certainly we're not making any product announcements at this point, but my bias has always been support managed and native, support cross-language, and so certainly that's the same kind of bias you should expect going into this. I would really personally hate to do something that was only for one language, and it's intended to be applicable broadly to others as well.
So it'll work native, managed, or unmanaged?
Yes, that's intended.
Okay, thanks.
Yes.
It's abstraction of Concur. But
okay, I better take only 2 more then. Okay, yes?
The problem is, when your program code is not running, then you go into debugger. And in the debugger, you see then typically what the compiler made as code, and you no longer see this abstraction. And then it's very painful today even concurrent programming debugging is painful.
Absolutely.
But with this concept, it's terrible. So
Absolutely.
my question is there parallel intentions that you said we have not have a new language, easy to read, easy to write. We have also a language easy to debug.
Yes. And in fact, concurrency is something that software companies, it's not just Microsoft, it's every software vendor in the world needs to deal with. And it's probably a bigger change than the OO revolution simply because languages can't ignore it. C could ignore OO and still be relevant. But no language will be able to ignore directly supporting concurrency and still be relevant for performance-sensitive applications just because it's going to be required. And that affects the whole stack. It doesn't affect just programming languages. It affects the runtimes that the last person just asked about. Is this a common runtime or is it only one compiler? So the idea is that it's better to be a common runtime, and you want the tools to make use of that as well. So your languages and tools are integrated. You need debuggers that can go back in time, that can replay messages, that can do causality tracking. So we understand all of those things, and so that's the kind of thing you can expect to hear more about probably at the next PDC.
I think it would be great when the standard would even say in a debugger you should find this structure, this type of debugging options or anything else that you can really go from one compiler to another and you see the same debugging model. And you have totally to learn everything else, yeah, from language to language, from compiler to compiler.
And so that's something that Visual Studio also tries very hard to do today as well, that you can write different parts of your program in different languages and just seamlessly debug through. So, yeah. I'm being cut off. Thank you very much for coming, and I hope this is useful for you. Please enjoy the rest of the conference.